Okay, so in this class we're going to derive the permutation formula using the first fundamental principle of accounting. So we're going to derive a formula for n permute or, this np or. Now, first thing, just what that means is if I look at something like 3 permute 2, what we're saying is if we have 3 objects, let's just write down letters A, B, and C, how many ways can I permute them, which just means arrange them? How many ways can they be arranged, taking 2 at a time? So from a population of 3 things here, I'm going to take them 2 at a time. And the key thing to remember with permutations here, when we're talking about permutations, is that AB, which is one selection of 2 things, remember we're only taking 2 at a time, is a different permutation to BA. And AC is a different permutation to CA, and BC is a different permutation to CB. And that all the permutations, there are 6 permutations. So what we're going to do is we're going to develop a formula so I don't have to write lists, because it's fine to write a list of 6, but what about when we get a bit bigger than that? Note there is a button on your calculator for permutations. On my calculator it's the shift function of the multiplication key. So if I type in 3 permute 2 and hit equals, it tells me 6. Okay. So we're going to derive a formula for this. And we're going to just look at a series of kind of examples, I suppose. So deriving the permutation formula using the first fundamental principle of counting. So I have a population here of 5 letters, and I want to arrange the above letters. If I take all 5, taking all 5, so actually we're talking about 5 permute 5 here. We're taking all 5 letters at a time. So what do I do? Well, I use the fundamental principle of counting, which says, break it up into tasks. Task 1 is to choose a letter to go in the first position. Remember, I'm just trying to arrange them. So A, B, C, D is a different arrangement to C, D, A, B, E, for example. How many ways can I arrange the above letters? I take all 5, so I have to take all 5. So, task 1, choose a letter to go in the first position. There are 5 ways to do that. Task 2, choose a different letter to go in the second position. There will be 4 ways to do that. Task 3, choose a different letter again to go in the third position. 3 ways to do that. Task 4, choose a different letter again, not already chosen, to go in the fourth position. There will be 2 ways to do that. And there will be 1 way to choose a letter to go in here. Remember, once I choose a letter for the first position, that means I've only 4 letters left to choose for the second position. Once I've chosen letters for positions 1 and 2, I'll only have 3 options remaining for position 3, and so on. Notice that is 5 factorial. And I'm actually going to write that as 5 factorial over 0 factorial. Remember, we defined 0 factorial to be 1. And note that 0 is the number I get. So 5 factorial divided by 5, subtract 5 factorial. 0 is the number I get when I subtract 5 from itself. Okay, and you can work that out. 5 factorial, 5 by 4 by 3 by 2 by 1, that's 120 ways. But this really is the one I'm interested in order to establish my formula, in order to derive the permutation formula. How many ways can I arrange the above letters if I take 4 at a time? I'm going to take them 4 at a time. I've got 1 less task, so I'll only have 4 tasks here. I have to choose a letter from the population of 5. The number of ways I can choose the first letter is 5. Task 2, choose a second letter. But I'm arranging them, so I'm rearranging them. I'm not repeating letters here, I'm just rearranging them. So task 2 is to choose a different letter to go in the second position, which will be 4 ways to do that, because I'll already have chosen one of the letters to go in the first position. For task 3, I choose a letter to go in the third position. There will be 3 ways to do that. And task 4, which is my final task in this case, because I'm only taking 4 letters at a time, is to choose a letter to go in the fourth position. There will be 2 ways to do that. 5 by 4 by 3 by 2. Notice what I have there is 5 factorial divided by 1 factorial. Because 5 factorial is 5 by 4 by 3 by 2 by 1 factorial. Divided by 1 factorial, it cancels the 1 factorials out, leaves us with this. If you're unsure about that, make sure you've looked at my last lecture on factorials and cancelling. And I'm interested in this 1, and note that's the same as 5 factorial. That 1 is the same as 5 subtract 4 factorial. And actually, that's still 120 ways. It's actually the same thing. But I'm thinking about it differently. Even though it's the same value, I'm thinking about it in this way. Instead of 5 minus 5 factorial is 5 minus 4 factorial. But because 0 factorial is defined as being 1, that's the same as 1 factorial on the bottom. Where it starts to change is now. In the next example, how many ways can I arrange the above letters if I take 3 at a time? Well, taking 3 at a time, I've only 3 positions to fill. I've still got 5 letters from which to choose. I choose a letter to go in the first position. Well, there's 5 ways I can do that, any of the 5 letters. But 1 letter will be chosen and will be used up by placing it here. So there will be only 4 ways to choose a letter to go in position 2, and then only 3 ways to choose a letter to go in position 3. And what I really want you to note about that is that's the same as 5 factorial divided by 2 factorial. Which is, and again I'm going to write this as 5 factorial over 2 factorial is 5 minus 3 factorial. And you'll find that 60 ways. By 4 by 3. But again, I'm not really interested in the 60. What I'm really interested in is this, because I'm trying to derive a formula. How many ways can I arrange the above letters if I take 2 at a time? Well, if I take 2 at a time, there's 5 ways I can choose a letter to go in the first position, and 4 ways I can choose a letter to go in the second position. And what I really want you to think about is 5 by 4 is the same as 5 factorial divided by 3 factorial. Which is the same as 5 factorial, and 3 is found by subtracting 2 from 5. And that's 20. But I'm not so interested in the 20 at this point in time. I'm really interested in this. So taking 2 at a time, we have 5 from a population of 5, of course. Population of 5, so we're always getting that population size on the top. But I'm choosing 2 at a time. I'm subtracting 2 from 5 on the bottom. When I was choosing 3 at a time, I'm subtracting 3 from 5 on the bottom. Choosing 4 at a time, I'm subtracting 4 from 5 on the bottom, etc. So NPR can be defined as NPR, N permute or. That's the way we read that. N permute or. It can be defined as N factorial divided by N minus or factorial. Okay, so 10 permute 2 will be 10 factorial divided by the difference between 2 and 8, or 2 and 10, which is 8 factorial. Remember that when I cancel, we'll have 2 terms. The biggest term will be 10. The smallest term will be 1 bigger than 8, which will be 9, which is 90. Or you can just type into your calculator 10 permute 2. Okay, but do get into the habit of working it by hand. So we have our goal, was to come up with a formula for NPR. We have NPR is equal to N factorial over N minus or factorial. Let me look at one more example here. How many 4-digit PIN numbers with no repetition are possible? This is really important, no repetition. So essentially, we've got 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. Not 10. 10 isn't a digit, of course. They're my 10 digits. So I'm looking for 4-digit pins where no repetition are possible. I have 10 digits and I want to take different arrangements using 4 at a time. So it's 10 permute 4. It's important that there's no repetition here. So 3, 1, 2, 4 could be a pin number in this case, but 3, 1, 1, 1 could not. 10 permute 4, well, my formula is that's 10 factorial divided by 6 factorial. Whereas 6, well, 6 is the difference between 10 and 4. There are going to be 4 terms in here. The biggest one is going to be 10. So it's going to be 10 by 9 by 8 by 7. Okay? So we can work that out by hand. 10 nines are 90. 90 times 8, 720. 720 times 7. 720 times 7, well, 700 times 7 is 4,900 plus 20 times 7. I'm getting 5,040 there. So there are 5,040 different 4-digit pin numbers with no repetition. Okay? How many 4-digit pin numbers with repetition are possible? Well, this is more tricky. What I'll do is I'm going to first look at all possible 4-digit pin numbers. Where some of them will have repetition, but some of them won't. It's obviously going to be bigger than 5,040 if I include all these. So I'm going to use the first fundamental principle of counting to establish how many 4-digit pin numbers are possible, you know, ignoring the with repetition part first. So all possible 4-digit pin numbers. Well, the first thing is to choose one of my digits to go in the first position, and then choose another digit to go in the second position, but the next digit can be the same, so I've still got 10 choices. Choosing a digit for position 3, I'm allowed to repeat, so there's still 10 choices. Choosing a digit for position 4, there's still 10 choices, so there's 10 to the power 4, or 10,000 4-digit pins altogether. Now, how many of those will have repetition? Well, we know that 5,040 do not have repetition. So, how many have repetition? Well, 10,000 altogether. I'm going to take away all the ones that have no repetition, leaving me with 4,960 4-digit pins that do have repetition. Okay, so that's slightly more complicated. In order to find out the ones that do have repetition, for example, 1, 1, 2, 3, that's a repetition there of ones, or 7, 9, 8, 7, there's one where the 7 is repeated. There's 4,960 of those 4-digit pins with a repeated digit somewhere in them. There's 5,040 with no repeated digit. That's all. They will either have repeated digits or they'll have no repeated digits. It's as simple as that. 10,000 4-digit pins altogether. Okay?